This presentation will discuss alpha carbon chemistry. We will discuss aldol addition, aldol condensation, Claisen condensation, and Michael addition reactions. The learning goals are as follows. After this presentation, you should know the mechanism, reaction conditions, and be able to predict the products for aldol condensation, Claisen condensation, and Michael addition reactions. What I want you all to focus on is that remember, all of the chemistry begins with the enolate ion. So if you recall in the presentation on last Friday, that remember the alpha protons of a ketone or an aldehyde are acidic. So whenever you have a ketone or an aldehyde react with sodium hydroxide, that you will have deprotonation and you will form the enolate ion. And this is resonance stabilized. So all of the chemistry begins with the enolate. So again, remember that the alpha protons are acidic. And so whenever a ketone or an aldehyde reacts with a base, then you have deprotonation of those alpha protons. Also recall that if you use a strong base such as LDA or sodium hydride with an aldehyde or ketone, that in solution, this is an irreversible reaction. The only thing that will be in the solution is the enolate ion. So in solution with a strong base such as lithium disopropyl amide or sodium hydride will only have the enolate in solution, versus if you use sodium hydroxide or sodium methoxide or methoxide, that you're going to have the enolate as well as the starting material in solution. So again, all of this chemistry begins with the enolate, which will be your nucleophile. So the aldol condensation basically is what we have when we have, in this case, we have an aldehyde reacting in basic conditions under heat. If you notice in the first part, the first three steps of the mechanism, first there's a proton transfer or deprotonation of those alpha hydrogens. So now we have the enolate form. So in solution, we have the enolate as well as our starting material. So the enolate does a nucleophilic attack to give us our addition product. Here, this is the carbon of the carbonyl, so we're forming a new carbon-carbon bond. So then here, the alkoxide does a proton transfer from water to give us our aldol addition. Remember that this reaction is occurring under high temperature. So it's involved in basic conditions and it's heated. So at this point, in the second part, we have the elimination of water. So remember, this is an alpha carbon, and whenever there's base, that there will be deprotonation of those alpha hydrogens. So hydroxide deprotonates or does another proton transfer. So we have here the formation of a negative charge. Again, this will be an enol. So what we have is the forming of the double bond and we have the loss of a leaving group. And this is actually goes into the forward direction because now we have a conjugated system, which is favorable and is downhill and it's a very stable product. So if you notice here, all of the chemistry begins with that alpha carbon, which is the nucleophile, which is the enolate. So we can also have cross-aldol condensate, cross-aldol reactions, simply because here we can have two different aldehydes, or in this case, two different ketones in solution. So we can have a possibility of 4 different aldol products. Simply because remember, all of these have an alpha carbon, which has acidic alpha protons. And so we can have the combination here of this of the two, we'll say in the two red, that actually gives us an aldol product. We can have two of the blue do the product. We can also have a red and blue form to give us an aldol product, or we can have in here where the red is actually the nucleophile forms the enolate and it does a nucleophilic attack on here on the blue aldehyde. So whenever we have a mixture of aldehydes or ketones in solution, we can have a mixed several different products. Again, and this is under basic conditions. As I stated here, the aldol condensation reaction will yield to give us that alpha beta unsaturated ketone. And again, remember we have an aldehyde, which we have the aldehyde part, and in here the alcohol, hence we have the aldol condensation. I want you to know that aldol condensations occur under acidic or basic conditions, and it's always heated. So when this is run at a high temperature under basic conditions, you will get an aldol condensation reaction plus water. So it's always performed at elevated temperatures, and in the case it's under basic conditions. So remember, you must know the conditions for the aldol condensation. It's under basic conditions and it's at elevated temperatures. So you will see heat there, and you will get this alpha beta unsaturated ketone. So remember, the aldol condensation occurs when the aldol addition is performed at elevated temperatures. So if we just have the reaction occur at room temperature, then we have the beta hydroxyaldehyde. If we do this under elevated temperatures, then the reaction will continue to give us the alpha beta unsaturated ketone. Again, here, this is our ketone, this is the alpha carbon, beta. So we have our alpha beta unsaturated ketones. And this is done at higher temperatures under basic conditions. Just like we can have, we can also have intramolecular, meaning that we have what? The ketones are in the same molecule. And this occurs when we have, this only occurs for 5 and 6 membered rings. And that is because they're stable. So remember, when you're forming ring structures, you have high energy species. So you have ring strain, you have torsional strain. So in the case when we have 5 and 6 membered rings, we don't have as much ring strain or torsional strain, because then the molecule can adopt a structure in such that we're releasing the ring strain as well as releasing the torsional strain. So it's a stable molecule. So when we have the ketones or the aldehydes in the same structure, we can form 5 or 6 membered rings. Again, this is done under basic conditions and at high temperature. So what we end up with is this 5 membered ring. So again here, this will be the structure is now structured that we'll see that we can see our 5 membered ring forming. So this is our nucleophilic site. So this is our alpha carbon, which has alpha protons, which are acidic. So deprotonation or proton transfer occurs. And again, it's lined up in such a way that then this alpha carbon can do a nucleophilic attack. Therefore, now we have this alpha beta unsaturated ketone, and we have a 5 membered ring. So again, let's practice, do some practice problems of predicting the aldol condensation reaction. So we're going to do an example where we have it's under basic conditions and heat. So the first thing that's going to happen is we're going to have our deprotonation here, and we're going to form here the enolate. So in solution, because we used sodium hydroxide, we also have some of our starting material. in solution. So we see here that we formed a new carbon-carbon bond. So what we have here is our aldol addition, but because this is run at high temperature and we still have, it's under basic conditions. So these protons here are acidic. So we have this negatively charged species here, and so what will happen is we'll form a double bond, and because we're now forming a conjugated system, we will get the following product. So this is our alpha beta unsaturated ketone system. So remember, you notice here that all of the chemistry begins with the enolate. So the enolate will do a nucleophilic attack on the starting ketone because in solution, because we use hydroxide, here we don't need that. Hydroxide, and it's run at high temperature heat, that we will get the condensation. So that means we're losing water. So we're going to get this alpha beta unsaturated ketone. And this is done under high temperatures. If it's done at low temperatures, then we're just going to get the aldol addition. So now that we see that aldehydes and ketones can undergo condensation reactions, esters can do condensation reactions as well. And these are called Claisen condensation. Again, all of the chemistry begins with the enolate. The enolate forms or performs a nucleophilic attack on the starting material. So again, if we use a base such as sodium hydroxide or sodium methoxide or methoxide, we are going to have in solution the enolate as well as the starting material. And in this instance, instead of it being a ketone or an aldehyde, it's an ester. So they can go reversible condensation reactions. And so basically what you're forming when you do a condensation reaction with esters, you're forming a Claisen condensation product called a beta ketoester. And so what we see here is this is our ester group here. And then in the beta position, we have what we say a carbonyl group or a ketone. So that's how we get that beta ketoester. So Claisen condensation is simply a nucleophilic acyl substitution reaction. So again, we see the nucleophile is the enolate of the ester, which is this group here. And then the electrophile is the ester. So the acyl group is this part here. So basically we can say we have an acyl substitution reaction. And so again, we have this alpha, in this case, we have this beta ketoester. This is called the Claisen condensation. And again, the nucleophile is the enolate of this ester. This is our alpha carbon. Here we have sodium methoxide, which deprotonates, so it does a nucleophilic attack. And so we will go through the mechanism. With the Claisen condensation, again, the first step is forming the enolate. So we have this OR. So it deprotonates the alpha proton, and so now we're forming the enolate. The enolate does a nucleophilic attack on the starting ester. So now we have this addition reaction. So remember that all ketones go through this tetrahedral intermediate. So then instead of protonation occurring, because this is run under basic conditions, so basically what we have here, we have basically stronger bases. And so what's going is that then we're going to have the reformation of our carbonyl group, and then we have the OR group that is, or the alkoxide, which is our leaving group. The last step again is the deprotonation. And so if you notice here, this is not an equilibrium. The base is actually used. So in order for us, the last step you'll notice is the proton transfer. So once this reaction is finishes, we have to add a mild acid in order to reprotonate to get this beta keto ester. So this drives the reaction to completion. The deprotonation drives the reaction to completion. So this is a downhill process. And so if you notice here, this reaction is not in equilibrium. The reaction goes mostly to the right. And so acidic workup is necessary because, again, this reaction is run under basic conditions. So the Claisen condensation has to deal with esters versus aldol condensation deals with aldehydes and ketones. The only difference here, Claisen has to deal with ester group. And if you notice again, the first step is the proton transfer or the deprotonation of the ester or of the alpha protons to form the enolate. The enolate does a nucleophilic attack. Here we have our addition product. Instead of getting the aldol addition, so to speak, which is similar to the aldol condensation, what we have is the reforming of the carbonyl group, and then the alkoxide is actually our leaving group, versus in the aldol condensation we saw that OH was the leaving group. Another thing that I want you to know, that when the type of base that has to be used, if you notice here that OR is used and not OH. If we use hydroxide with an ester, what will form is hydrolysis. So the hydroxide would do a nucleophilic attack on the carbonyl of the ester group. So with Claisen condensation, you usually use the same base as the ester group. So in this case, if this were OMe, your base should be OMe. If this is O, in this case, with an ethyl group, then your base should be OET, so that transesterification does not happen. What I mean by transesterification is that here, your ester group can change. So if you started out with methoxide and used ethoxide as your base, then this group will no longer be OMe, it will be OET. And so we could have transesterification. So whenever you're doing a Claisen condensation, you want to make sure that your base is exactly the same as the ester group. So again, there are some limitations. So in this case, the starting material must have 2 alpha protons, because the removal of the second proton by the alkoxide, it drives the equation to or in the forward direction. Secondly, as I stated before, you cannot use hydroxide because we will have hydrolysis, which is what we see in this reaction. So instead of here the enolate being formed, then the hydroxide will do a nucleophilic attack on the carbonyl group of the ester group, and we end up with hydrolysis, which means that the Claisen condensation will not occur. Thirdly, we want to make sure that the base that we're using with the Claisen condensation so that transesterification does not occur is the same group as what's on our ester group. So if this is an ethyl group, you want to make sure that your base is ethoxide. If it's a methyl group, you want to make sure that this is methoxide. Just as we can have intramolecular aldol condensation reactions, we can also have intramolecular Claisen condensations occur. And this is called the Dieckmann cyclization. Remember, 5-membered rings and 6-membered rings are very stable. And this means that your esters are within the same molecule versus 2 separate molecules. So here, you always number your carbons. And so again, we find our alpha carbon. And again, we will have the enolate. And if you notice here that our ester group is ethyl, notice that the base is ethoxide as well, so that transesterification does not occur. With that being said, we see that we can form, we know what our product is. So here we have this beta keto ester. This is my alpha carbon, this is my beta carbon. So we see here that 2, this is my alpha carbon, did a nucleophilic attack on carbon 6. So now we have a bond between carbon 2 and 6. So if we see that our esters are within the same molecule, we can have intramolecular condensation reactions. If we see that our aldehydes or ketones are within the same molecule, we can have intramolecular condensation, aldol condensation reactions can occur to give us a 5-membered or a 6-membered ring. So let's do some practice problems predicting the type of base that is used, and then we will go over the mechanism. So if we recall, with the Claisen condensation reaction, remember the base that is used with the Claisen condensation must be the same as the ester group of the ester. So if this is our ester, here the first step is what base should be used. At the end, it should be followed by so what we're going to have is this beta keto ester. So remember that the base that you use for the Claisen condensation must be the same as the group of the ester. So our base here would be so that transesterification does not occur. So what if we have what base should we use? Again, in order to get our beta keto ester in this sense, it would be that's the base we would want to use. We want the base for the Claisen condensation to be the same as that of the ester group. So remember, when you have the Claisen condensation reaction, that you're going to get a beta keto ester formed. So again, everything begins with the enolate. So again, you find the alpha carbon. The alpha carbon has alpha protons, which are acidic. So this would be the enolate that is formed once it reacts with this ethoxide. And then that will do a nucleophilic attack on the starting ester. The last reaction that we will discuss is dealing with conjugate addition reactions. So if you recall, alpha, beta, and saturated carbonyls are made via the aldol condensation. So remember, if an aldehyde or a ketone is treated with the base under high temperature conditions, that we're going to get this alpha, beta, and saturated ketone product. And what I want you to recognize here is that alpha, beta, and saturated carbonyls have 3 resonance contributors. So if we look at this, remember that you have the enol here. So we have this carbon, which can be electrophilic. And so now this is one resonance structure here where the electron density is mostly on this oxygen. So if you look at this 3 system ring here, this is very similar to an allyl cation or an allyl radical. So therefore here, this pair of electrons can go in between these 2 carbons, and now we have what? An electrophilic carbon. So when we look at alpha, beta, unsaturated ketones, not only is this carbon of the carbonyl electrophilic, but we see that also this beta carbon is electrophilic. So whenever we react an alpha, beta, unsaturated ketone with a nucleophile, it can attack here at this position or at the beta position. So what I want you to recognize that this is basically a 4-system conjugated or 4-member conjugated system dealing with 1, 2, 3, 4 atoms. So basically we would start, this is 1, 2, 3, 4. So this is a pi conjugated system. So we can have a nucleophilic attack either at the 2 position or the 4 position. So this is something that's very important about alpha, beta, and saturated carbonyls. And this has to do with its resonance structures. So you'll see that here that this carbon is electrophilic as well as the carbon of the carbonyl group. So whenever an alpha, beta, unsaturated ketone reacts with the nucleophile, you can have addition at the second, at the carbon of the carbonyl group, or either at the beta carbon. So if we look at this, when we're talking about a conjugate addition reaction, so the general mechanism is as follows. So if we have a nucleophile, so if you recall here that both the carbon here and the carbon here are electrophilic because of their resonance structures. So the nucleophile attacks here at this beta carbon. So now we can have what? This is now, so the nucleophilic attack occurs here. So now that electron density can go here due to one of its resonance structures, forming the enolate. Again, we can have a proton transfer, and so what we have is the enol. So through tautomerization, if you recall, with the enol, the ketone is more stable than the enol. So now what we have here is a nucleophilic attack here at the beta position. So this is the general mechanism for conjugate addition or conjugate nucleophilic addition or attack. So we've already done examples of Claisen condensation reactions. So let's look at conjugate addition reactions. Stronger nucleophiles tend to attack at the carbon of the carbonyl group, and less reactive nucleophiles tend to do conjugate addition reactions. So if we look at typical enolates, they often give a 1,2 and a 1,4 addition reaction. Stabilized enolates, such as this example here. So if you recall, the first step is deprotonation. So this is my alpha carbon. I have alpha protons. Therefore, this negative charge is not only delocalized with one carbonyl group, but it's delocalized with two. So the more resonance structures you have, the more stable this enolate is. So in this case, it will do the 1,4 addition. So therefore, we see a nucleophilic attack here at this beta carbon. And so after that, we have pronation with an acid. And so this is our 1,4 addition product. This 1,4 addition product is called the Michael addition. And so when we look at Michael additions, we have something called a Michael donor, which is the nucleophile, which is the enolate. And then we see that the alpha beta unsaturated carbonyl group is the Michael acceptor. That's basically the electrophile. So remember, nucleophiles donate, it has electrons, and then in this case, the Michael acceptor, which is basically the electrophile, is the alpha beta unsaturated carbonyl. This is a chart that actually gives us a look at the Michael donors. So these will actually give us exclusively give us the 1,4 addition. So this means that the enolate will attack at the beta carbon. So we see all of these are our Michael donors or nucleophiles, and then we have our acceptors. So we see alpha beta unsaturated aldehydes or alpha beta unsaturated ketones, alpha beta unsaturated esters, alpha beta unsaturated amides, alpha beta unsaturated nitriles, or in this case alpha beta unsaturated nitrates. So these are our Michael acceptors. So whenever we have conjugate addition reactions of the enolate to alpha beta unsaturated systems, these are called Michael addition. So let's do an example of a Michael addition. So again, we will have our Michael donor, which you see here, we have an alpha carbon that's in between two carbonyl groups, and then it will react here with our alpha beta unsaturated aldehyde to give us the following product. And so this is our Michael donor or electrophile, which is this alpha beta unsaturated ketone. And here we have our this is our Michael acceptor, and this is our Michael donor, which you can say is our nucleophile. So first, again, we have depronation of these acidic protons. This is our Michael donor. It does a nucleophilic attack, and it's going to attack at the beta carbon here to give us our Michael addition. So again, know that Michael additions, you usually have a nucleophile or enolate that's in between two carbonyl groups. If we look at that chart there, we have very stable enolates. So anytime we have, examples, if you look at that chart there, you're going to have alpha carbons that are in between two carbonyl groups. So we can have, in this case, a diester. So this will be considered to be a very stable because again, we have an alpha carbon that is in between two carbonyl groups. So this negative charge is not just delocalized over one carbonyl group, it's delocalized over two. So if you recall, the more resonant structures, the more stable that ion is. In summary, I would like you to remember that treatment of an aldehyde or ketone with the base will result in an aldol addition reaction, which is basically a beta hydroxyaldehyde or ketone, which will give you your product. Whenever you treat an aldehyde or a ketone under basic conditions and it's heated, you're going to get the condensation reaction, which will result in an alpha, beta unsaturated aldehyde or ketone. We can also have cross-aldol condensations, meaning you can have two different aldehydes or ketones in solution, and if you treat them with a base, sodium hydroxide, that you can have cross products. Also, you can have an intramolecular aldol condensation reaction, and that will give us a 5-membered or 6-membered ring. And this is due to the fact that you have your aldehyde or ketone are in the same structure. So you'll get a 6-membered or 5-membered ring. Claisen condensation has to do with ester. It undergoes the same attack by the enolate, and this is just dealing with esters. So remember that you must use the alkoxide base, which is similar to that of the ester group. If you use a different base, then you're going to get transesterification. You cannot use sodium hydroxide because that will give you hydrolysis of the carbox of the ester. Therefore, you will not have your Claisen condensation reaction. Remember, alpha beta unsaturated ketones are formed from the aldol condensation reaction under basic conditions, and it's heated. So if you have an aldehyde or a ketone that possesses an alpha beta unsaturated system, remember that they are susceptible to nucleophilic attacks, and this will occur at the beta carbon. So this is called the conjugate addition or the 1,4 addition or the Michael addition. So remember that the nucleophile is called the Michael donor and the electrophile is called the Michael acceptor. So remember, with Michael additions, you must have an enolate that is in between two carbonyl groups. So the main thing I want you to remember is that all of the alpha carbon chemistry begins with the enolate.